Gotta check my mic. Maybe not. Should work right now. Hold on. Let's try this one more time. How is the sound sounding? Is it sounding far away or as good as usual? Hopefully better than usual. And then we're going to check the chat. Good. All right. Thank you. It's this microphone dance that I have. I have a headphone, I have a microphone. It's a thing. Okay. So let's see what we have here. I'm going to go pretty much now, actually. Let me just start presenting my screen here. So this fun stuff. Actually, I should switch over to this thing first. I'm torn with the way I want to approach this particular lecture, simply because we finished at a weird kind of place. And let me throw out what we were finishing last time. That's what we were finishing on last time. Also, let me bring up the. I'll bring up the chat. There we go. All right. So last time we were here, we talked about all sorts of weird, wonderful things. I know, very exciting. We were talking about data, and you know how everyone loves data. I ask my sons what they want for their birthday. They say data and an analysis of data. Uh, Good times. What actually was happening? We were looking at and sort of methodically approaching how we look at data and what kind of data that we have. So we had different types of data. We had grids, we had tables. So grids are you choosing how the thing gets how it gets interpolated, how you discretize the space of the data. We talked about tables, which is just, I have this data table and this is the corresponding value, much like what you'd get from a database. We'll look at that a bit more today, actually. We talked about geospatial or geometry in general, which is some kind of spatial representation, and that's where you're perfectly okay to use 3D. Spatial information should be represented the way the spatial information was stored. If it's a 2D map, you represent it in 2D. If it's three-dimensional, then you represent it in 3D. And we had networks, which is like a graph. It's who's connected to what, what's connected to this. Okay. And then we looked at attributes, and then we talked about the fact that our attributes can also be broken down into parts where we had quantitative, quantitative is the more general term for continuous data or discretized data or discrete data. So we had data that 1, 2, 3, 4, 5 is discrete data. You don't have 1.5, it's 1, 2, 3, 4, 5, but it goes off to infinity both directions. And the difference between 1 and 3 is 2. There's a known distance between the intervals. Ordinal data is weird. It's things where you have small, medium, and large. The difference between small and large is not two. It's two. There's two steps in between, but the difference between a small and a medium, I don't know what it is. It's fuzzy watercolor kind of thing. Um, if you wanted an example of that, for those you took that took 1400 with me, that would be one how we were grading the labs, right? We would say you either did a reasonable job, you did an exceptional job, or you didn't do a job at all, right? There was no like 52.5%. There wasn't an 89.6%. It was did a good job or not, and there was different levels, but the difference between those levels was hard to quantify. And then we had nominal data or categorical data, two different words for the same thing. And that would be things like countries. That would be things like your student IDs. That would be things like, I don't think of a good example of this. What would be different than that? Things that there's no real ordering at all in them. So different degree programs in the university. There you go. Right? There's no real ordering. Even if you think your degree program is better than other people's degree programs, there's no real ordering. And so that's where we were sort of looking at things. And we also looked at the fact that when we have something like this, different data, different attributes map to different visual representations, but want some better than others. And if you approach it in a methodical way and you say, I know exactly what this kind of data is, it is categorical data, I should be using, let's say, hue to represent that data. If I try and use hue for quantitative data, I will have things to say about it, right? I mean, that's sort of what we're looking at here. Uh, Mapping the right kind of data to the right visual representation is the job, essentially. Design is not guesswork. It is not your gut intuition. It is a sort of, at least in this field, a methodical approach to figure out what works in what situation. Okay, it's like the right tool for the job. So we looked at position being critically important, also critically important for all of these things. If you throw away your position information, have a reason for throwing away the position information. Position information is critically important. And we talked about different ways of doing things. So if I have categorical data like types of birds, whether I use different size circles or days of the week for, say, I'm hoping this would be considered ordinal, but you can consider discretized or discrete data. Uh, but months would be different, right? January, February, March, the distance between the months is different. Sometimes it's 31 days, sometimes it's not. Um, you can consider that ordinal. It's always that sort of judgment call on your part to a certain extent. But if you were encoding it left to right, or you're encoding with larger and smaller, it implies something. And we also notice that area is great for quantitative. It's pretty good for ordinal, right? It's not great because Monday is not better than Wednesday. It comes first. That's the reason it's ordinal. There you go. Right? There's an ordering, but yeah, but it's really going to throw you off when you use it for categorical, right? Monday is not better than Wednesday, but Eagle's certainly not better than Hawk, right? They're just birds, unless you're really a big Eagle fan or you're from Philadelphia, uh, right? It doesn't make the difference what kind of bird we're talking about here. All right, area, as in different ways of representing the data look different, like as in work differently. That's what we also pointed out. So this is where we left last time. I wanted to do an in-class exercise, and I'm going to start the ball rolling with this. We're going to take maybe 5-10 minutes. We're going to throw it into lecture 6, uh, although we didn't put in lecture 5, so we'll count these up anyways. But so I'm not sure if we have time to break into a group. We're doing light and fluffy. We're not even going to do the full redesign. So I can't scratch these things out, but we are not going to do the full redesign, and I'll see if I can fix this in a second. Uh, but I would like you to, again, try and critique visualization. And that could just be some jot note form. So we're doing it intentionally very quickly. Just so, yeah, let's throw it in lecture 5. Let's keep it in lecture 5. So in lecture 5 in the Google Drive, we're going to view this visualization, see how well you can look at it. Hopefully you can read it. You can also just grab the slides online. Uh, and then and then you're going to critique what you like about it, what you didn't like about it. Just throw it in a Google Doc, throw it on there. All right, you ready? You can also work in groups if you want. That's perfectly okay with me. If you have some kind of text message, or if you want me to assign you to groups, that's fine. We can do that. Um, I just would be random groups. I think that might be harder to deal with. So rather than a group, you can work in a group if you want, but you can also work alone. So hopefully, there it is. So I don't know how much you can see of this. Hopefully you're seeing it full screen. This is meant to be computer science as a subway map. There you go. So we have fundamentals of computer science that connects to statistics, which also then is connected to programming with this line, including data frames, readings, CSV data. How that's computer science. We did that in 1400. Hypothesis testing, Monte Carlo methods, because they're one and the same. Um, Prediction, lift, that's so machine learning algorithms, text mining, machine learning. Here's visualization stuff over here. Here's big data. Here's toolboxes of code, data ingestion. I would like to see what your critique of this is. I intentionally chose this because we're looking at queue, we're looking at position information, we're looking at connectedness, we're looking at a whole bunch of these different things. So what is it? Uh, so again, that's just the view of everything here. What do you see? How is the work organized? What's the purpose of the visualization? Is it successful? Right? What I want you to particularly focus on is the kind of data that we're dealing with, like categorical, ordinal, quantitative, data type, and data sets. Right? We're just going to spend about 5 minutes doing that. I'm going to mute, but I'm going to answer any questions you guys have as they come along. And then we'll pick up to what the main part of the lesson is after that. But I like giving you guys something to practice on in terms of what we just covered. And if you don't know what I'm talking about, please ask, because I know some people will sit in silence. So please ask if you're confused with what we're trying to do. We're doing a critique. We're throwing into lecture 5. You can work solo or you can work in a group, and all you're doing is critiquing this thing. That's why I wanted to throw it out there again. We're just doing a quick and dirty, like 5 minute analysis. Okay, I think I messed up something here. Interviews were in lecture 5, so we don't want to use that again. It would have been lecture 4. So let's just throw it into 6 and be done with it. I want to go back and fix my slides here in a second, but if anything, lecture 4, we have code to do is lecture 4, so let's make sure it was in 6. All right. So let me make sure I fix this. case I'm doing the same thing. So, okay, actually, I wasn't muted. All right, good to know. So I would like you guys to pass in whatever you have right now. Just we're just meant to just be playing around with this a little bit, and I don't see anything so far. But maybe I just it hasn't been it hasn't sunk yet, synchronized yet. That or there's only four people. I only see four faces on the call so far. So maybe there's only four of you in the entire class. Thank you. All right, we finally got one. Thank you, whoever the first person for in-class exercise. Madison. Thank you, Madison. Other people, please post some stuff on this. I actually want participation, and I might lock out. Actually, I plan to lock out some of the earlier in-class exercises. I'll lock out this one too. So I'm more than happy to do that once the class is over. So in case you're thinking, hey, I'm going to sneak one in later when I make it right. I don't want it right. I want it gut instinct here. Okay. Yep. Okay. So Madison's comments were various branches of the system are color coded, which helps organize the data. Great. If you want to consider those categories to be categories, because those are what you how you're viewing parts of computer science, then absolutely it's categorical data. Let's organize it that way. I may see many lines almost that are positioned in random ways to showcase the data. Overall, it looks quite busy. Yeah. Why is it looking quite busy is the other part of the question. The work is coded though various levels starting at one that you must go through of the data system. All along the way, it appears that every single piece of data is listed beside the white marker. And the question is, so if we start off at, okay, I don't know. You know what? I think I was interpreting the data wrong, and it's interesting at least. So you would start off with fundamentals. You would learn matrices and linear algebra fundamentals before you learn anything about computer science. Linear algebra and matrices. Yes, we're doing it wrong, it seems, according to this person. Hash functions, binary trees would be next in fundamentals. Relational algebra and database basics. The inner outer joins and theta join, and cap theorem, tabular data. Yes, these are all things, by the way. Entropy, data frames and series, sharding. I will make one particular bold claim here. Those are not fundamentals. Considering I don't know what half of those things are, or I don't know how to do half those things at least, Yeah, that's not a fundamental for everybody in computer science, and this is one person's opinion on this one. I would say that it would make sense if these were sequential and you had to do one after the other. Sure, sort of, but I propose that that's not in fact the case. Is to show the ordinal list of various components of a computer system and schema. It's not per computer system; it's the topic of computer science. But yeah, I would. But is it ordinal? You are, Madison, you are 100% right, assuming that it would be ordinal. In fact, that is a great way of looking at this because the logical person would look at this and say, these must be ordered and they're put in that order for a reason. And my claim is, no, they're not put in any particular reason. It's haphazard, and yet you read it as ordinal because of how it was represented. This is a beautiful example of that. Of if you present the data wrong, it sticks. You read it wrong. Uh, Specific pieces you need. At first glance, it's very crowded and hard to read. I'd say it's almost impossible to read, and the text is all over the place, right? And why? What's position doing here, by the way, out of curiosity? All right, so Cato, lecture 6, channel marker size. Too much text, it's crowded. Some visuals don't connect, so put those separate. Like a subway map, so information follows a path, but should it? It would be a network, but is it? It's actually not networked at all. You guys are all interpreting as network, and rightfully so, but it's actually not networked at all. Sharding has really nothing to do with multidimensional data modeling. Sharding has nothing to do with matrices and linear algebra, very little, and no more than other things. Random variables is one of the other parts for statistics. Uh, Reporting these and visual analytics, I'm assuming JSON and XML is in there. Nothing to do with linear algebra. Oh, the stars, I think, are the percentage of your path that you have completed, somewhat chosen at random as well. It looks like because it's like a 30%, I see a 15%. Uh, yeah, and this is, I guess, to learn all of computer science to get 100% to be completionist in computer science, you need to do all of these things, according to this random person I've never met online. This is just me making fun of somebody else's visualization because I'm a jerk. Let me also ask, what's position? We have connectedness. Subway map, and for a subway map, position actually does convey something. It conveys the general geometry of the area that it's twisted, it's morphed so that it's not exactly realistic. That's what a subway visualization is. It is the map of your city, but you're allowed to straighten out the lines to make it easier to read because who cares if the subway turns along that line? Who cares? You don't need that piece of information. You want this point, approximately where they are on the map, not exact path because you can't get off the subway halfway, right? So you might as well straighten out that line and make it look as clean as possible. That's what a subway map visualization is all about. It's a network, or it's a network, also a geometry at the same time, and it's trying to simplify it because you're underground. It doesn't matter what the actual exact map above ground is. Nice. Okay, let's see. Uh, so by the way, so far so good, guys. I'm very impressed for liking this. So I don't want to first thing I noticed is very busy. This might be like a cute classroom poster, but it would be fundamental, be more functional and interactive. Yep, agreed. Maybe put groups and connections first. Yep, definitely agree. The groupings are important, and you put them on a subway line. And are there actual? I can look at it again. And by the way, make sure your names are on this so we can actually give you credit for all the work that you're doing here. Um, in the list. Yeah, that's how I do it exactly. I'd have the group and put a list of all the different topics you wanted as a group. Because I will tell you one thing, this thing, there is no connection necessarily between machine learning, well, text mining and machine learning connect, I guess, but statistics and programming versus like visualization, machine learning, text mining, all of these other things. Visualization is not connected to anything else in computer science. That makes no sense. Right? It's just arbitrary. It's inaccurate data, and yet you're inferring actual cause and effect. You're inferring connectivity that's actually not there. The effect that this builds up to 100%. And where's HCI? Oh, yeah, there's not even in there. But visualization is an entire branch for some unknown reason. Lecture 6, please. And please submit to lecture 6 on the drive. I know, I know. I changed it later, so I'm just being mean. Perfectly fine question. All right. I wanted to go fairly quickly on this because we got a lot of ground to cover. But this is what I mean. You guys pointed out exactly the right things about it. There's a whole lot of flaws about it, and we also noticed the way you interpreted it and assumed that this person was doing it right is based off of how they represented the data. I fell for a bunch of stuff. You fell for a bunch of some different things. We all fell for some part of this, assuming that there was a rhyme and a reason to what they were doing. I assumed that this connectivity had something in common. I didn't realize that these were supposed to be sequential, which they probably should be, and yet there's actually no sequential ordering. Yet you consider this sequentially ordered. You can presumably this is all categorical data. There are different categories to look at in under that field, and yet you're just reading them one after the other, and you assume that the one leads to the next one because that's what it should. So I wanted to yell at somebody else's design here. So I wanted to get to, well, I want to show you this first before, if you guys can see what I'm doing here. We're going to look at parallel coordinates today, and this is just an interactive version of parallel coordinates rather than me having to find this thing again later on in the lecture. So as I roll over a particular area, whatever line I'm on, it selects all other lines that are in the same category. Parallel coordinates, you can zoom into parallel coordinates, you can do a bunch of things with it, but we'll get to that now. So, because we're looking at visual encoding today, which again relates to data, and we're about to transition right over to perception after that. So here is what we've been doing so far. We looked at what data is being shown, like looking at how we process, analyze, how we consider or think about our data. We looked at why someone's looking at it. That's what the whole task analysis thing was. That's what P2 is all about, which I hopefully will read very, very soon. If you have any clarification questions, please pose them because I want to make sure you know what we're trying to get across here, right? We're looking at your data, how it's being used, why someone is looking at it. We had some great clarification questions from you guys over the past couple of weeks about your project and how there were some really great interviews, by the way. And how we present the data, we haven't even really gotten to that. We did some fundamentals, but we're going to get to that nitty gritties of that later on. But we have to know what the task is. We have to know what the data is. In fact, we have one more part about what the data is, the abstraction of the data. But we abstract our data, figure out what the task is, then we figure out how to present it. That's our design methodology. So in task abstraction, we were looking at, is it for consuming the data? These are very high level things. Is it for consumption of data? Is it for somebody else to look at the data? Or is it for you to produce new data, derive new data from it? Is it for them to discover it, or it's just to sit back and enjoy? Right? Those are different tasks. And if you don't know what your task is, you're not going to present it correctly. If it's supposed to be on a phone while the person's running to catch a bus, it's very different than planning out your bike route. Or we were one group is looking at construction on the roads and seeing how it disrupts walking and commutes. Or looking at the frequency of sidewalks and construction in the city of Ottawa. Great. How often are they doing that? They might do that on a fairly regular basis because but you want to do it quickly because you just need to do a quick scan. You want, oh, my commute's going to be disrupted today. You're not going to be spending 40 minutes looking at this, but your commute might be disrupted today. If you're looking at I need to have names for the groups, by the way, just in case you're wondering. So group one, group two, group three doesn't is not as cool as like you guys having a cool team name. I like team names. I'd love you guys to come up with a team name. I'll discuss that in a bit more soon. Uh, so if we're talking about people looking at uh, temporary or recreational activities in Ottawa, they're seasonal based for one, but most people don't have to rediscover where their hockey rink, local hockey rink is. Right next to my house, there's a little hockey rink that they just plop down in the wintertime, and it goes away in the summertime, and now it's baseball time nearby. If I want to find where my hockey rink is, I do that once in that season. That's it. And I might do it again next season. But it's not a repeat thing that you would do for a community. And both are fine. They serve different purposes. Then we looked at data types. And that's what we're going to extend today. We looked at things like categorical, ordinal, discrete, and continuous data. I've already reviewed all. And then we looked at things like tables, networks, how things are connected, fields, that continuous data, like if I have a physics simulation and air flowing over an airplane wing, you discretize the space, right? You could also do that with COVID-19, trying to figure out what the frequency of infection is in the city, or frequency of contagion in the city is, by taking a subset of the population, and you're visualizing that. Or maybe visualizing only parts of the city and to show how bad it is. And then we also have geometry, which is you're going to overlay with all of these other things, and that's things that have a spatial component to it. And we also talked about the fact that your data, your task, and who your user is ultimately decides how you design things. So we're looking a bit more at the data, but you need to know who your user is and what their task is to know what their background is if they can understand your visualization, right? If you're a physicist, you have a very different, and you're looking at a physics visualization, it is very different than my mom looking at, email trends, right? Very different tasks. You don't have the same tool for that. And also just the data itself. So when we talk about data itself, what the data itself is tells you how to encode it later on. Okay, but what we're going to look at is the idea of sort of keys and attributes for how they represent visualization. Essentially, we looked at the attributes. Now let's look at how we define what the different buckets are, what the different elements, items are in our visualization, and how we can arrange it based on the key and spatial options. And we're going to look at some statistics as well. So be ready to cry. No, it should be fine. But we're going to look at some statistics and how things get distributed, just to give you another, this somewhat of a grab bag of different topics that before we get into perception. And then we're just going to do a full blown look at a slew of different visualizations, and see what your favorite one is. It's fun. So I want to get something first, and let's see. I want some participation on this one. It just can be in the chat. That's fine. We're not going to be submitting anything to the drive even. We're just trying to figure out, because God knows I don't know I wouldn't know these terms necessarily off the top of my head. What we're going to do a matching game. So what of these categories down at the bottom, what is this one on the left-hand side? The X, Y, and this thing, this sort of olive green thing. Which one of it? Is it a bubble chart, area chart? Area chart. Great. Nice. How about the next one? I think that's bar chart. It's a grouped bar chart, right? They have these groupings. Right. Next, we'll get there's a harder one in the next slide. Waterfall. Yeah, it's not one of my things. Business analysts and people that look at stocks love waterfall charts. I've never used one myself in my life. Yes, waterfall, because it goes up and down like the stock market, and you actually use two different colors to show whether it's going well or going positively or negative, which is kind of weird. There's no granularity. It's just good or bad. There's no in between. There's no like sort of good. Next one looks like a pie chart though. That's what threw me off. Got to be a sector graph, because we know what the other one is. So yeah, sector graph, because it has different height in there as well. So the sector could be different lengths. And then finally, we have our bubble chart. Great. How about this one? Oh, sorry. I need this part. There you go. So you know what the Venn diagram looks like, presumably, but what's this next one? The first one that we have on our list. Yeah, nice. How did you know there was a star plot? Good for you. I don't know. Polar coordinates, I would normally call them, but or polar graph. Um, and then we have a Venn diagram. Fine. It's a heat map. Yeah, it's called a star map because it forms a glyph. Based on how that works, it starts looking like a star because it does this little jaggedy thing. Yeah, agreed. It doesn't make sense as, as a visualization name. That's why I was like, how are people going to get this off the top of their head? How about a heat map? Where maybe I should go, what's the next one? It's not a heat map, by the way. Fox and whiskers, right? We're going to look at that, what that actually entails soon enough, but maybe you've already seen lots of these. Some whiskers. Next one. It's one of my favorites. Yeah, parallel coordinates. As in each one of those rows, A, B, C, and D is an attribute, and the lines are our items. And by doing that, you can present a whole lot of different attributes all at once, and you can see you can see patterns in the data. It's really interesting. At least I find it interesting. And there's our heat map, which does not look like really a map at all, but it is a two-dimensional, it's a grid or matrix, and then you color in the different cells in the matrix, and it looks sort of like a heat map. Well, that's why it's called a heat map. So here, what are we going to do with our tables? Well, first of all, we're going to talk about what the heck we're talking about with tables. One way to look at this, and many, I think you guys have done a database class, right? Correct me if I'm wrong. Yeah, okay. So you probably know more about this than I do. Yeah, I taught some kind of database stuff, but not deep dive into it. Normally with a database, what do you have? You have tables of data. You have normally you oftentimes you'll have a primary key. Sometimes you'll actually have tertiary keys, so multiple different attributes that define each row in your database. Right? Each row in your table, sorry, table I should say, can be uniquely identified either by a single key, a single attribute, or a single item, or multiple different items that describe what that, but uniquely describe each row in the table. If you don't have some way of uniquely describing each row in the table, you're doing it wrong, essentially. You got to make sure you have something that uniquely describes it. We're going to look at it from that sort of perspective again. Each row has a series of things that will uniquely identify it. We also have attributes of it and sort of data associated with each of these rows, but we're just going to visually represent it. So what can we do with our database or with data from our database? Well, first of all, visually, we can either separate them out. We could try and order things so that it is growing in terms of order of where the, let's say y, starting y, it's the maximum y value for each of these different attributes, right? We can order it based on the minimum y value for each of these attributes. We can order these things in terms of size or area. We could order these, we can arrange our data in all sorts of different ways. It doesn't change the data at all. The data is still the same. We can move them around, we can rearrange it, we can align it so that we can have an easier time reading it. It doesn't change the fundamentals of the data itself. And then we have how many keys we actually have. We actually have a zero key option as well, where you could have duplicate data and that's fine, right? If I have multiple tables being read in at the same time and no, they're no longer, there's it's nothing to uniquely identify something, that would be a zero key table. We'll look at one of those. But normally we have this would be when we have a primary key, right? I have a list of different items. I just go one after the other. If I need multiple dimensions at once, I have essentially two-dimensional or two keys to uniquely identify a given cell. Three keys, which so forms volume, and then maybe it's recursive. So hierarchies in Amazon or your file folders would form this sort of thing. How do I find um, this particular option or this particular item in Visual Studio? It is I go here, then I go here, then I go here, then I go here, then I go here. Right? That the word options could be in multiple different trees or multiple different menu items in an interface, right? The word edit could be multiple different places in a menu item. Edit for the text is different than edit for the project, for example. So it's not uniquely identified by one thing, it's hierarchically identified. It's not even identified by just a couple attributes. It's in menu, then under this, then under this, then I find my item. But really, I like primary keys. Primary keys are my friend. So a key, it's an independent attribute that uniquely identifies. So it forms a unique index, a unique way of identifying the row that you're looking for, the data that you're looking for. And if I don't have that, how the hell do I find what I'm looking for? Now, you could say from a database standpoint, but from a human standpoint, I need the same thing. I need to identify this particular student, or maybe I need to identify this particular group of students. Maybe I need to find, um, so let's see here, the set of concerned students that I have for all my classes. It's not unique. It's not, they're based on their ID. It's not based on the course. There's a bunch of different things that uniquely identify the students. It is their grade point average that I calculate. So I have to find uniquely identify the students with an ID, and then I also need to filter it out based off of how they're doing currently in the course. Our keys are almost pretty close to always categorical or ordinal. The one exception when we look at time series. So the vast majority of the time we have categorical data or ordinal data to identify a key. And then we have a bunch of attributes that form the series of cells in the on the row. And that can be anything, any kind of data you want. It can be categorical, ordinal, or quantitative. So when we looked at this last time, we noticed something. We looked at this like, here's our order ID, here's our order date, here's a bunch of different things. And we said, okay, well, this is ordinal data here. This product containers an ordinal data. Product base margin, that's quantitative. It's actually continuous data in that any level of precision that you want. We have shipping dates. So that would, I would say that quantitative data. It depends on how you want to view dates. Order priority is definitely ordinal data. Um, what's our key? Ah, yeah. Unfortunately, I think it actually has to be the first three rows. It's a tertiary key. Tertiary? Not one primary key. Maybe four. Yeah. You need to be able to identify a single row and 32, 32, 32, 32. This would be a terrible table in a database if I'm looking at this as a primary key because I have duplicates. Yeah, I don't like it when I have duplicates, but that is what we have in this particular case. We do an outer join, we'll get something explosive like this. So there is no single key for this because I have 35 twice, I have 32 four times in there. Things to worry about. How about this? Well, actually, the date works wonderfully for a key. In this case, there's no duplicate. It uniquely identifies a row. If I have any duplicates, then it can't be a primary key. But I can't use precipitation because it's not ordinal data. I can't consider ordinal data or categorical data. I can't do high temperature because it's also continuous data. By the way, these are degree programs at Northeastern. I just didn't change them. So here's a bunch of names. Now, these are terrible, names would be terrible for student IDs if you hadn't noticed. In this case, it works fine. They're all categorical data. It's text string, but it uniquely identifies the person. But it's a terrible ID in general. That's why we have student numbers, because David Sprague does not uniquely identify me. My ID, I don't have a student number here, but my ID number does uniquely identify me. No one else has that exact number. So if I have no keys whatsoever, I get this. This is where the scatter plot is your friend. Okay. If I can have duplicates of the same data point, they overlap, just two rows with identical data, or the attributes I'm showing are identical, I need something like a scatter plot. I can't do a box, I can't do a bar chart, I can't do a line graph because I have duplicates. There could be duplicates. So a scatter plot ends up being very, very useful if I'm doing with this kind of data. Scatterplot would be wonderful for that ordering and the size of the box and that previous example we had. Now, if I have one key, that's where bar charts come in, right? I have each bar is uniquely identified. Each bar in the x coordinate is my primary key, and then I have some attribute that I'm representing in the y-axis. So that's why we like them, because we know exactly what the bar is and we know what we can read off the value. Similar with line graph, there's actually no real difference except for line graphs can do time series or more continuous data on this axis down here if I need to, but I can't have duplicates. So normally time series or discretized data. How about this? Well, actually, we've already seen an example right here. Boom, matrix is a 2D arrangement of two keys at once. But we can do more examples. So here's one stacked bar chart. Grouped bar charts would also work for this sort of thing. I have two different attributes. I have that uniquely identifies this value here. It is both what of the two groups I'm in and another key. This is maybe it's men and women, and this is year of in university, right? So if you're a woman and you're first year, this is the value, or this is whatever value we're reading off. Same thing here. It's not uniquely identified by one key, it's two keys to identify the value. Or we have heat maps, right? I represent one direction, I represent in the other direction. This cell is uniquely identified by this and this. So at this row and at this column, uniquely identifies this cell. And then we can visually encode things on that particular cell or put a value in that cell. So matrix would be another example. Or this would be another example. Here we have a time series going left to right, and each one of these bumps in the scheme graph encodes some category of information. So if I want to find out what, I'll give you a better example here. If I want to see how much I now pronounce you Chuck and Larry, if anyone remembers that movie, oh good God, or I Am Legend or Enchanted, let's say, American Gangsters here. I can't believe National Treasure Book of Secrets is that high. It made that much money. Cannot believe this. But this is how much the movies make at a given time. So you take a particular week vertically and which particular movie, and you can read off how much money it made in the box office for that week. So Ocean's 13 did not, well, Ocean's 13's cut off. It's over here somewhere. Okay. National Treasure, it made a lot of money in the month of December, near Christmas time, just before Christmas time, and then immediately just went to nothing. Alvin and the Chipmunks also made a lot of money, it seems, or a fair bit of money. Right? You're just looking at the height at any given time, and that uniquely identifies the data that you're reading off with two different dimensions we're talking about. Here's probably a better example because it also tells you exactly what we're talking about with these slices. This is from the New York Times as well. You can even look at it. So I haven't actually tried this, but let's try it. Go New York Times membership. Okay. You should be able to interactive for running. Here we go. Oh, there we go. Now it's interactive. So we see the individual Olympics. This is Tokyo 1964. This is Mexico City 1968. And we can see how each country did. for the Olympics. But the important thing here, what really stands out here is World War II. First of all, they did cancel the Olympics at some point, at one point in time. Berlin, 1930. Where's Berlin here? Anyways, we the Berlin Olympics is right here. So I don't know why. Oh, it's because this one's not interactive yet. Is it Nazi Germany? That's one hell of a way to start the Olympics, or what put an end to the series of Olympics in a row. But here is the United States boycotting the Olympics in Moscow. Notice how much the Soviet Union, how many gold medals and medals in general the Soviet Union won. And this is Soviet Union boycotting the Los Angeles Olympics in 1984, and how much the United States did as a result. Okay, and you can look at the individual sports and how they have changed over time, including Finland, how they're doing in the marathon. Finnish the Finns were very, very good at the marathon until what, the 1980s. I didn't even know that. Look at Ethiopia taking over. That's incredible. Okay. Anyways, there's some really interesting stories being told here. Um, but it uniquely identifies we need a date every 4 years. We have a date, and we need the country or a set of countries that we're looking at, and that uniquely identifies the data you're trying to read off. And now you have to figure out how you want to represent data in a two-dimensional array or two-dimensional basis. They're two keys essentially. You can also just arrange your tables. So this is a bunch of students, random students in math, physics, dance, and drama, because those make sense. And we're looking at what their what their averages are in different degree programs. Well, this would be a scatter plot matrix. I get do a scatter plot, so I do represent math and drama, and then dance and math, and physics and math, and math and math. So I have math and math, physics, dance, drama and drama. So the same on both axes along this diagonal here. So notice you should always have this perfectly straight line along the axis, because you're mapping the same data to the same data. This is exhaustively outputting all the different ways I could arrange and make a scatter plot. So I make a matrix of scatter plots. The important thing is you can then see if there's relationships between different types of data. So for example, dance and drama seem to be somewhat correlated. It will look better, even better, if we had a nice tight correlation. Dance and physics seem to be inversely correlated. Well, if you're good at dance, you seem to be bad at physics. Here's the other way you can do it. So I can arrange my data in a bunch of different ways. So in this case, it would be each line is a student, and this is their average in math, physics, dance, drama. And you can start seeing trends and patterns in the data. We've talked about what kind of data we have. Now we have to worry about how we orient our data. There's three different ways we're going to do that. We have rectilinear. That's the one everyone's used to. So I put it in some kind of matrix, good enough. Surprisingly, not everyone can actually read these things. Not everyone feels qualified in reading them. They get okay with a bar chart, but then they get really confused with scatter plots. It's very, very common for people to have trouble with reading data. We can also look at it in terms of parallel coordinates, or parallel was representing the data. And then we can also look at radial fashion. Those are the three big ones. So we're going to look at this. So we looked at how many different keys we had, but then how we orient our data is a different thing. So here's rectilinear. So all I have is I just put them in order. A line. Maybe it's a matrix, maybe it's a rectangle, but it's what you would normally do, some kind of grid pattern, right? Up, down, left, right. Here's radial. Same data set, just in a radial pattern. Where this gets used oftentimes is often for a lot of glyphs that we have. So pie chart actually is a radial version of things, but we can do it in a whole bunch of different ways. So the star coordinate, radial. right? You're drawing, the idea is that I'd have center point, and I'd say on this axis, this person is represented on this axis here. Sometimes I'll have a whole bunch of attributes, one, and then this will be the person themselves, and then I will draw out the attributes along different axes around in a circle. But radially arranging things throws away position information. It gives me length, but it throws away the position information for a lot of this. It doesn't, unless I arrange the positions on the circle, it's harder to read. That's why we tend to like rectilinear. And here's another version of rectilinear. This would be the canonical example of a scatterplot matrix. So let me try and, nope, that's the wrong one. Yeah. This is an actual data set because people are nerdy. And this would be, so this is a scatterplot matrix of people and flipper length, body mass. Oh, wow, this is a different data set. Cool, okay. This is a new data set, not the standard data set for this. The ORCID data set, what you were seeing before, the ORCID data set's the famous example, but let me just show you what we're talking about here. This, when we talk about brushing and linking later on, this is what brushing and linking is. I select in one matrix, and then the corresponding data in all the other matrices show up. All the other data sets and all the other scatter plots get showed up in in the matrix. So I can look at, let's say, this subset of the data here, and I'll see the corresponding data in all the other matrices, all the other scatter plots in the matrix. There you go. This, by the way, what I was trying to point out is this is the famous ORCID data set. It's very, very famous, where they map out the sepal width, the sepal length, the petal length, and the petal width for a bunch of orchids. Yes, somebody measured flowers. That's what they were doing. I don't think scientists do. Anyways, so they measured out a whole bunch of orchids, and they were trying to categorize orchids based off of this data set, and seeing if you can group the orchids based off of their petal width and length and the sepal width and length. And this is what you end up getting, where you're trying to see if there's groupings. And yes, there's a group here, there's a group here, there's a group here. And those groups sort of group together. They're different types of orchids. You can actually categorize orchids based off of these dimensions. There's a correlation between them. But again, notice this is sepal length and sepal length. That's why it's a perfect line, because of course it's a perfect line. But as soon as it's sepal length and sepal width, it doesn't form a perfect line anymore. Here's a radial visualization of types of cookies. It is very scientifically rigorous for how long you can leave your cookie in your tea or coffee before it cracks and breaks. It's stupid data, but I like it just the same. Right? But here is length of time, how long you can leave it in before it breaks, and what kind of thing is. And by the way, for those of you that these are British cookies, and if anyone's watched Flushed Away, this is what an actual jammy dodger is. It's those little cookies with the jam in the center. I did not know this until I watched, I think, Doctor Who. It's, yeah, little cookie with a red jam in the center. In case you're wondering if this is a new trend, no, this is Florence Nightingale's visualization of army deaths in the East, showing what is the cause of various deaths in the army using this kind of stacked radial representation of data. It's a beautiful, beautiful visualization drawn by hand by an. Or we can arrange it in parallel coordinates. And this is one of my personal favorites just because I'm nerdy. The idea is, again, each one of A, B, C, and D are different attributes. And each line, the line, instead of being the time series or something like that, what normally it would be representing an attribute, a series of attributes. The line itself is the item, the row, if you will. the person, oftentimes in your data set. And then the different attributes are the lines themselves, the rows. By doing this, it allows you to see a whole lot of things at once. But this is probably a better way of describing it. So here is a whole bunch of cars. I'm looking at the number of miles per gallon it drives. Here's the number of cylinders it has. Notice 8, 6, 4. There's really no need for 7.5. There's no 7.5 liter car. How much air it displaces, how much horsepower it has, what year it was built. And if I select 1982, I will see the number of 8-cylinder cars, 6-cylinder cars, and 4-cylinder cars, how much fuel economy it gets, that sort of thing. And I could brush and select parts of it. But notice if I arrange the different rows, it doesn't change my data. If I move the year all the way over here next to cylinders, it allows me to find correlations and connections between number of cylinders and the year a lot more easily. It doesn't change my data at all. The data itself stays the same, but arranging it in a different manner tells me different things. And how do I, if I have multiple keys at once, how do I handle it? Well, this is just one of the many ways. Lineup is one of the, I think it's just a cool visualization, but this is your university in the United States, at least at the time, your university and what its school ranking is, and then world university ranking for it, how much of its academic reputation is, the faculty of arts, faculty of humanities, international reputation, that sort of thing. Then it's how it's changed over time from between 2011 to 2000 and before. And then you can actually just follow how it these trends over time. So essentially you're representing it all, and then you're using connections to show how it's changed between 2012 and let's say 2010, following the path. There's a bunch of different ways. And if you have some crazy data set like this, let me know, because it's hard to get your head around. And I think finally, before we get to what we're actually going to be doing, okay. And somewhat finally, the one little exception to our rule is time series in terms of the key. The reason it's our exception to the rule is because it is continuous data, but we discretize the space. We don't have infinite precision in our time series, even though we think, time can be considered infinite precision. One of our big common things is we would say, hey, by the year or by month, and we group it, we just separate out the different months. So we get quantitative data over time, but we use it as a key. Most of the time, our keys are categorical or ordinal, except time is our one exception for the most part. Okay. So, and then by the way, we can order things, and that helps us understand things. Ordering and rearranging our data itself helps us with our analysis process, and giving people the ability to do that changes how people look at the data and process the data. So that subway map that we were looking at, the subway map of computer science topics, if you could arrange things and filter it and move things around, you'd have a very different approach or a very different interpretation of that data set as a result. Oh, sorry, it's not the last one. This is our last one, the one that comes up and it's kind of weird and kind of fun. So divergent data sets. It's one of the times where we have to use a different, despite having continuous data or discrete data or whatever the case is, where we have to take a different tact on how we represent our data. A divergent data set, normally if we are using color, for example, oftentimes we'll use saturation and it'll go from like white to red. It might go from black to white, it might go from different levels of blue, different shades of blue, different brightnesses of blue. Divergent data sets are slightly different because if I use a hue, for example, or a color, I diverge in two different directions at the same time. I'll go from extremely dark to lighter red, extremely dark red to lighter red, or extremely light blue to dark blue. Or I could also arrange it so that it goes in two different directions and I have a clear center point. I need different for divergent data sets. It's the one time I actually need different. I sort of want different visualization techniques. So in case you're wondering what the divergent data set here is, it's whether you run a deficit. So here are the different blue and red versus for the Republican Party versus Democratic Party. And so you're clearly identifying what party affiliation you are. And here's the deficit being brought up by individual people. Notice that Barack Obama, I think that actually went down afterwards. I'm not 100% sure on this. This is Great Recession. Immediately afterwards, there was a whole lot of stimulus, and then they brought a lot of that money back. But I think it's still, a lot of it did stay behind. And Trump would, I think, goes well past that one now because of COVID-19. But notice, here's Harry Truman bringing the most money in, but that's 1949 to 53, immediately after the war. And suddenly people are having baby booms and their industries humming away, and they just have money pouring in essentially from taxes. Dwight D. Eisenhower is still doing well. Bill Clinton actually reduced the deficit. And then you get someone like, but here's the average Republican, here's the average Democrat. And you're seeing divergent because the center line is zero. Anytime you have a zero center line and you go in two different directions, a divergent system makes sense. And you can either use color, you can use position, you can use area, but you have to think about what that center point is and base it off of that. So you diverge based on color, you diverge based on space. Okay, I talked a lot, I realize, in a row. So I want to see what I'm going to do. Actually, I think what we should do instead of jumping into this, I have a whole bunch of. Let me show you what I was going to do. We're looking at mode, median, standard deviation, blah 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 blah. A lot of math. I love this image, so just in case to point out, we will get to that later. I want to sort of break up the lecture because I think it's pretty dry right now. So and we're looking at these sorts of things. And by the way, yes, these are all these data sets, all of these points all have the same mean X value, mean Y value, same standard deviation, same Y standard deviation, and same correlation. They're all this in terms of descriptive statistics, they're all the same, including the dinosaur. Yes. So in case you think you can't lie with statistics, here's a classic example. All right. I would like you to look, let's do this one instead. Although this is an option, but you don't have direct access to the data set. I would like you guys to look at the DataViz project and the datavizcatalog.com. And I'm going to try and make another folder in the drive for let's call it lecture 6B. And we're going to throw stuff in there. I would like you guys to just play around for a little while. We have 10 minutes left, and we're going to see what kind of visualizations you've seen, which ones you like. And I would like you guys, what I'm hoping for, you can either look at datavizcatalog.com or the DataViz project. It is a slew of different visualizations just to get a feel for what people have done before. Oh, sure. Thank you. That's a great idea. Is project.com and I think I need the www in this case. Just look at the various visualizations that they have available to you just to see what kind of things they have. They are not all wonderful visualizations, but and what I'm going to do right now is I'm going to go make a new folder, and we're going to just make a file and paste the URL for your favorite visualization and put your name on it. Okay, just to get a feel for that sort of thing. Okay, so let me stop sharing for 2 seconds here. Okay, I made a new folder called Lecture 6B, Favorite Viz. Just throw in something like your favorite visualization in there. Let me resume sharing. So it would be right here. This one. There you go. I'm kind of curious myself to see what we have here. So data viz project. Um, there we go. These are just examples of what they've come up with over time. Mhm. Polar chart. That's what I call it instead of a star chart. Oh, yeah, I want to spend about 5 minutes talking about some of these. So uh, just let me know. So try and post it as soon as you can. Just look around. But I want you guys to have a feel for what's been done before, what kind of options you have available to you, but not it's not something to panic over. All right, let's pull. I'm going to pull up some of these here. Even I think you were the first one in, so I didn't pick on you today, so. Oh, it's an exploding visualization of, so what, you can either do it in the chat, but what are we looking at here?
Hello?
Yep.
Uh, so from what it's part of, so it's part of, sorry, it's part of a series of a bunch of exploding diagrams
Listening?
from, it's called Taken Apart. If you click on the link, it doesn't really provide much of a description on it, but it's part of a collection called Infographics for the People. With the source at the bottom there.
Mhm.
But from what I gather, this is a look at oh, what is that logo? Oh
GE,
my god.
General Electric.
General Electrics, yes. The inside of a modern day windmill and sort of
Mhm.
the main, what it looks like the main motor on the inside there and the revolving parts around the outside that control the actual movement of the windmill itself. I
Mhm.
think it's really cool because it actually shows you, like, instead of, we always see just the windmills spinning from the outside, but we don't actually know what goes into, building them or what's actually going on in the inside. So I think this is really cool. I personally did not know what this is what like windmills looked like on
Oh,
the
that they would have a
inside.
giant metal coil inside for just generating
Yeah.
power.
No, I honestly didn't know that.
Giant
It's pretty
magnetism.
cool.
Oh, and you could have looked at blueprints, right? Yeah, and it is very pretty. You're right, Tori. Uh, but you could have looked at little blueprints, but notice that with an exploding chart, you're still getting the three-dimensional aspects and how these different levels are connected as well. But you'll also notice the issue with exploding charts. The GE logo is blocking this part right here. This metal bar is blocking this part here. There is always some occlusion with an exploding. It's that finding the right angle, the right amount of explosion to break it apart is actually a challenge. But it's a very useful technique for showing how things are made or how things are composed, like a cruise ship, for example. Now, this is an exploded version, but it's the slices of the cruise ship as you go. This could be angled and exploded in different ways. Here is how a computer is made, for example. Um, it's just a technique for if you're wanting to see how the various parts all fit together. It's a, it's a very useful technique. It's very common, but it's very it's very it's a nice technique for what we're if you're trying to look at something that's complicated and has a bunch of moving parts. Let's see who else have we not picked on. There we go. Favorite viz. There we go. Picking on random people that I don't normally pick on. Unless somebody wants to be picked on, I'm more than happy to. Oh, nice. So what are we looking at here? Session. You can either talk or you can just chat. Yeah. So what are we looking at? So this is under network map, right? So we can have a look at. Let me see if I can get Fishbone. Transit map. It's not a transit map. And pin map. Nope. Connection. Oh, it's more of a connection map, isn't it? The reason I had to clarify that though. Yeah, it's this is it actually migrations? Yeah, it's main migration house. Nice. Very nice. I didn't read this. That's awesome. The reason I pointed out at this that it's a connection map instead of a network map. Networks don't necessarily have a geographic. component to it. This clearly has to have that in for this the map. So you have to, it's constrained by spatially, so you can't put things wherever the heck you want, but you're also trying to show the number of people that are that are moving. Notice the thickness is using that. It's then notice the kind of data that we have. We have quantitative data. So thickness is useful for quantitative data. Also, we have different categories for whether it's Western Mediterranean, West African, where ultimately they're going to, I do believe, right? And so you have different categories or based on the destination. And so you're using color in that. It's categorical data. And you also have the distance that they're traveling, but naturally being based on the map itself. Uh, so yeah, I think that's awesome. Like it. Also intriguing. I'm going to stare at this for a while now. Nice. Um, Anything particular that you really liked about this kind of visualization? Okay, just letting you know for future reference for your final projects. I'm not poo-pooing anyone's ideas or anything like that. Uh, if you get to the end of the project and you say our visualization is pretty though, it will not carry any weight on that one. Right? There's a utilitarian aspect to it, and it is pretty, absolutely. But there's a utilitarian aspect. You're actually able to read off critical pieces of information from it while looking pretty as well. Uh, well designed, but you need to be able to justify what you're doing as you go. Yeah, clear, easy to see, functional. You what kind of inferences you're going to make about migration patterns across the world, where they're predominantly going, where they're coming from, where they're going to. Right? These are all parts of what this thing in a simple little visualization does. But breaking it down into the various components is what we're looking for your later parts of your project and for your critiques. So this is why we're doing these in-class critiques, is just to get the practice to be able to look at something and go like this is wrong, this is great, right? So we want you guys to get into that habit. All right. We're out of time now. It's 9:57. When we come back next time, we will look somewhat at statistics, and then we're going to deep dive into perception and cognition. And I'm going to nerd out with my psych degree stuff. So it you'll hopefully see the world in a different way and how we actually see things. So it should be exciting. Thanks everyone, and I will talk to you guys later. This Thursday's lab is going to be D3 and how to program. So if you're concerned about that at all, that's what the lab is all about. All right. And thank you very much and have a great day, guys. Thanks.